Hi, today we will learn chapter 17, which is on thermal behavior of matter. PV equals nRT or PV is nKT. Here K is Boltzmann's constant. Another way to express this law is PV equals nRT. The same thing. N here is mole, the unit is different. And K, here N is just the number of K over R is mole. 1/2 mv square is average, what is it? Average kinetic energy, right? Average kinetic energy per molecule. So we can conclude from this derivation and the empirical law, because these two should be equivalent. So then we can find that actually, what is the temperature of a gas? The temperature of a gas is nothing but average kinetic energy of the molecule. So from this derivation, we can learn that meaning of the temperature of gas, for example air, is the average kinetic energy of the gas molecule. So 1/2 mv square is 3/2 kT. Kinetic energy is just x, y, z translational motion. So from this, we can find that this average velocity of a single molecule is related to square root 3 kT over m. But does it mean that all the molecules move with this speed? No, it's just average speed. Actually, in fact, molecules should have some range of speeds, has some, distribution of speeds due to the random collisions among the molecules, and also some molecule will move slower than the other. Some molecule will even move faster than this average speed. So up to now we learned the ideal gas law. Now phase transition. As temperature changes, not only material changes their temperature, they can change their phases. There are three fundamental phases of materials. Most materials occur in three phases, which are, as you're familiar, solid, liquid, and gas. When the materials change their phase, their temperature doesn't change, but they require energy. Let's say water. When water from ice to change to water, even if the temperature doesn't change, okay, at 0 degree C, because the melting temperature of water is zero temperature at atmosphere 0 degree C. So temperature, even if temperature doesn't change, it requires energy for the ice to change into water. This energy that is required to change phase is called heat of transformation or latent heat. And during this phase change, even if you provide energy to ice, the energy is all consumed to change the phases from ice to water, so the temperature doesn't change. Same here. From water to, while it's boiling, temperature doesn't change, but all the energy is consumed by changing the phase from liquid to gas. This energy is required to change phase. So there are names. From solid to liquid transition, we call this latent heat as heat of fusion. From liquid to gas, heat of vaporization. Solid to gas, heat of sublimation. Sublimation means phase change from solid to gas. For example, CO2 in atmospheric pressure is instead of become the solid, CO2 solid becomes liquid, it just evaporates. So sublimation occurs instead of fusion for CO2 in atmospheric pressure. Most importantly, temperature remains constant as all the energy goes into the phase transition. During the phase transition, what happens is for example, solid to liquid, it breaks the bond. Liquid has looser bond than the solid. So energy is required to break that bonds. And gases has even loose, they don't have any bonds. So to break the liquid has still has some bonding between molecule, but to break the bond completely, it also requires energy. So that is a heat of vaporization. So for typical materials, these are the phase diagram between pressure and temperature. As you increase the temperature, there's most materials has this triple point. Triple point means gas, liquid, and solid coexist. Okay. all three phases coexist in equilibrium. That point is called triple point. And as you can see, so let's say here, as you increase the temperature, solid becomes liquid and liquid becomes gas as you increase the temperature. Why? Because as you increase the temperature, the material acquires more thermal energy, right? Heat. It uses the heat to transform its phases, break the bond from solid to liquid and then liquid to gas. So normal substances, normal materials, as temperature increases, phases changes from solid to liquid and then liquid to gas. And also, see here, at a constant temperature, if you increase the pressure, normally gas becomes liquid and then solid. Why? If you increase the temperature, pressure, so the distance, inter-atomic distance becomes less and less, so it tends to form bonds. So gas becomes liquid and then solid as you increase the pressure. This is normal for typical substances. And above the critical point, above some point, gas and liquid is not really well separated. So sharp distinction between liquid and gas disappears. That point is called critical point. So at very high pressure and very high temperature, they're not really just a solid because they still move vigorously. What is the difference between the solid and liquid? It maintains the shape. Right? So, but because due to this high temperature, there's no even solid, but it's not exactly liquid because it's somewhere between these two. So that point is called the critical point. So according to ideal gas law, if you increase the temperature, right, and for example, if the pressure is the same, maintains constant, what happens is volume increase. So that means if you increase temperature, then it expands. So this is thermally, if you give some thermal energy or increase temperature, then most materials expand. This is called thermal expansion. And also liquid and solids are also expanded when you increase temperature. Okay? We define this thermal coefficient beta. How do we define it? This is the definition. For 1 Kelvin increase, for 1 degree C or 1 Kelvin increase temperature, how much volume ratio changes? That's this volume expansion coefficient, ratio of volume, okay, per 1 Kelvin increase of temperature. And this is three-dimensional. For one-dimensional solid, for example, for rods, we can only consider, we can approximately, there's no one-dimensional material in this world. All materials are almost, there's one-dimensional material, a single molecule line, but usually rods are, we can approximate rods as one-dimensional solid. So then it can characterize by linear expansion coefficient, which is we only consider the length expansion coefficient instead of volume expansion coefficient. So alpha here is length expansion coefficient. For cubical volume, which has the same length in XYZ direction, the expansion coefficients are related. Volume expansion coefficient, which is defined as this, 1 over V, delta V over delta K, which is dV, same thing here. And we can divide this delta L, dL in the denominator and numerator. Then dL dt here is related to length expansion coefficient, right? And dV dL is 3 for the cubical volume. It becomes, this is alpha, right? So it's 3 alpha. So usually for isotropic materials, volume expansion coefficient, isotropic material means expansion coefficient is same for XYZ direction. Then volume expansion coefficient is 3 times length expansion coefficient. Here's the end of chapter 17. We learned ideal gas law and phase changes, phase diagram, and also thermal expansion of usual substances and also water. Thank you.